In the last lecture module, we looked at the structure and elements of standard form categorical syllogisms. Now we want to turn our attention to that effective decision procedure that's the real payoff. Recall that Boolean and Aristotelian interpretations differ by conveying less information. The Boolean interpretation indicates validity without any conditions, but it's a smaller class of arguments that it can recognize as valid. By conveying more information to the Aristotelian assumption, Aristotelian logic recognizes more forms as valid. But many of those valid arguments are valid on the condition that the classes satisfy the Aristotelian assumption. In order to modify our effective decision procedure to accommodate categorical syllogisms, we're going to have premise and conclusion diagrams with 3 circles. The subject of our conclusion, the minor term, we'll put in the bottom left-hand circle. The predicate of the conclusion, the major term, we'll use the bottom right-hand circle for. And the middle or bridging term that is in both premises will always go up top. And we'll arrange these circles in this fashion so that every possible relationship between the minor, major, and middle terms has a place in our diagram. So the middle term by itself is area 1. The intersection of the minor and middle terms that excludes the major term, that's area 2. The area in the circle that includes all 3 terms, that's area 3. The area that has the middle and major terms but excludes the minor term is area 4. Area 5 is the minor and only minor area. Area 6 is the minor and major area that excludes the middle term, and Area 7 is the major term only. Incidentally, it's this graphical nature of our proof procedure, this requirement that our circles in our Venn diagram intersect in every possible way with one another, that puts a limit on our ability to use Venn diagrams for more complicated arguments within categorical logic. Once we get past syllogisms, where we have 2 premises being symbolized using 3 classes and 3 circles, things start to get too messy and difficult to use easily, and we start to lose that simplicity in order to try and gain complexity. Now, when we symbolize arguments using these Venn diagrams, especially when we're symbolizing premises, we want to use the universal premises first. So we'll always symbolize universal premises first, and we'll always focus on the 2 classes that a particular premise is relating, and not pay attention to the other classes, particularly when we're symbolizing universal premises. We'll shade in the area that we would normally shade if we were just doing a direct inference. So all of the area that we would normally shade when we do a universal statement relating 2 classes together will get shaded in these new Venn diagrams. However, when we have a particular statement, we're going to have to be much more careful. Every area in our modified Venn diagram where we would put an X has been divided in 2 as a result of adding that 3rd class. So if we look at the intersection between S and M, it now has 2 distinct areas. If we have a premise that says some M are S, we know that it goes in the intersection between M and S. What we don't know is whether it's also a P, and as a result, we won't be able to tell if there's nothing else in our diagram whether or not the X goes in area 2 or it goes in area 3. In those circumstances, when we have 2 open areas and we need to put an X in, we always put it on the line so that we know it goes in here somewhere. It could go here or it could go here. Either way will satisfy that premise or conclusion statement. Let's look at some examples. Suppose I've got a statement that says all S are M. If I'm starting in Boolean logic, I'll say, I don't know if there are any S's, I don't know if there are any M's, but what I do know is everything that's in the S circle, if there is anything, would also have to be in the M circle. And so all of that area of S outside of M would have to be empty at minimum in order for this premise to be true or this conclusion to be true. So I would shade it in, that whole area, including that part that's overlapping with P, because all of the S, if there are any, are going to have to be an M, and so everywhere outside of M has to be empty. If I have a statement that says no S or M, and I'm being a good Boolean, I'll say I don't know if there are any S's, I don't know if there are any M's. But what I do know is there can't be anything that is both in my S circle and in my M circle. And therefore, the intersection there between S and M would have to be empty, and so I'll shade that area. I'll shade the S and M area, and I'll shade the S, M, and P area, because those are both areas that are in S and in M, and if no S or M, there can't be anything in either of those areas. Let's try some more. Suppose I have a premise that says all M are S. If I'm a good Boolean, I say I don't know if there are any M's, I don't know if there are any S's. But what I do know is everything that is in that M circle, if there is anything, would have to be in the S circle. And so that area of M outside of S, that has to be empty. So I would shade it in to indicate that that has to be empty. Suppose my other premise says some M are P. This is a particular statement, so I'll say to myself, okay, there's at least one thing. It's in my M circle, and it is also in my P circle. And that means that it's got to go somewhere in this intersection. Now, I can't put it in here because all this area in M outside of S has to be empty, and so it can't go there. And as a result, I know exactly where it goes. I put it in the one open area in the intersection between M and P. Suppose I have a premise that says no M are S. Again, as a Boolean, I say I don't know if there are any M's and I don't know if there are any S's. But what I do know is nothing that is an M can also be an S, and therefore that intersection between M and S would have to be empty. Suppose I have a second premise, and that premise says no M are P. So I'll be a good Boolean and say I don't know if there are any M's and I don't know if there are any P's. But what I do know is that there can't be anything that is in both the M circle and the P circle, and therefore that area would have to be empty. So I'll have to shade it off like I've done there. Suppose I have a premise that says all S are M. Well, then I know that I'm going to have to shade that area in S and outside of M, because it would have to be empty for this premise to be true. Suppose my second premise says some M are P. I know there's at least one thing. It's in the M circle. It's also in the P circle. Now, when I look at that intersection, I say there are two different possibilities there. It could go here, it could go here, or it could go in both of them. Right? I don't know. Nothing about my premise tells me, and so I put that X on the line to indicate it's got to go in there somewhere. Either way, either area, as long as it's in M and in P, it doesn't matter which area the X goes, it will still make that premise true. But the premise doesn't tell me which area it belongs in, and so I leave it on the line. Suppose I have a premise that says no S are M. Again, since I'm a good Boolean, I say, look, there can't be anything that is both an S and an M, and therefore that intersection would have to be empty. Suppose my second premise says some M are P. Well, then there's at least one thing. It belongs in the M circle. It also belongs in the P circle. Now in that intersection, I say, it can't go in this area because this area has to be empty, has to go somewhere in here. Therefore, there's only one place for it to go, and I'll put it in like so.